She's a force to be reckoned with. Yeah, she's one of a kind. Got that confidence and style. She's blowing your mind. With every step she takes, she's owning the scene. A queen in her own right, living her dream.
Hello everyone, welcome to my YouTube channel. Today in this video we will discuss on the concepts of backpropagation with a clear and practical example. In our discussion we will see steps in designing a neural network having 4 inputs with bias, 3 neurons in the hidden layer and 2 neurons in the output layer. Backpropagation is nothing but just after feed forward and calculating the total error. Finally, this obtained error will be propagated from the output layer through hidden layer to the input layer for updating the weights so that the error will be optimized. And let's jump to the Python code on the Spider IDE. Okay, before directly go to the code, let me explain the neural network that is going to be designed. Okay, so the first thing, we have 4 neurons in with the bias. The bias here is x0 and the 3 new inputs x1, x2 and x3, and we have 3 neurons in the hidden layer, and there are 2 neurons in the output layer. Okay, x0 is given to both the hidden layer and the output layer, and these desired values d1 and d2. Okay, here we have 2 outputs values, and we will generate y1 and y2, which are compared to the desired to get the final error. Okay, so now we can jump to the code. Let me explain all. Okay, so the first thing is just import a library. That is what we have done. It's just we have to import the numpy as np and import this MATLAB plot library as plt. This is because we are going to draw the error graph. Okay, and the next thing, we will give the input values in the variable called x. These are arrays as numpy.array of these values. Okay, that is, assume this one is x1 and this one is x2 and this one is x3. Okay, and here we have the variable y having these d1 and d2 values. This one is d1 d2 for x1, this one is d1 d2 for x2, this one is d1 and d2 for x3. Okay, this LR is nothing but is learn coefficient. Okay, we are using there, and so the next step will be just assigning parameters. Okay, we have input size 3, yes, x1, x2 and x3, and output size, that is 2, d1 and d2, and the hidden layer having 3 neurons. Okay, and so we will initialize the weights, that is weight 1 and weight 2, b1 and b2. Okay, weight 1 is the weight that is in the first neuron. Okay, now let me show you in the figure. So here is weight 1. Okay, the weight 1 value here is, and here is we have the weight 2 values. Okay, so weight 1 is we are generating the random value for weight 1. Okay, so np.rand of uniform size, self input size and hidden size. Okay, the size of the w1 will have 3 by 3. Okay, here we have 3 input size, and here we have 3 hidden layer. This uniform keyword is used to get the value of w1 between 0 and 1. Okay, so the same thing will be done here in w2. That is the second weight, that is random value, that is between hidden layer and the output layer, that is will become 3 by 2 size. Okay, this b1 is also the bias weight. Okay, which is 1 by hidden layer size. Okay, here is so b1 will be here we have b1 value with this 1 by the hidden layer size. Okay, hidden layer size is 3, so the size of the first bias will be 1 by 3. Okay, and b2 will be 1 by output size, that is 1 by 2, that is the bias weight. Okay, so the next step will be just the feed forward. Okay, that is forward propagation. Propagate the input x1, x2, x3 and then up to the output value. Okay, so self.z is numpy.x and w1 plus this one. This means guys, the dot product of the input x, okay, x contains x1 up to x3, and it's the weight values, okay. The first weight times this dot the input value plus the b1 will give the first z value, okay. And self dot z2 is the sigmoid value of this one, okay. That is the output of z will be, and the sigmoid value of this self dot z, okay. And self dot z3 would be the dot product of z2 with weight 2, okay. That means the output value of hidden layer will be given to the output layer, and this must be multiplied by this the second weight and add the second bias, okay. And the last is output, okay. The output y1 and y2 are sigmoid values of z3, okay. After multiplying or the dot product of z2 with the second weight, we will generate the output value, okay. So this output value is then compared with the desired value to get the error, okay. This is all during the forward propagation of x input, okay. And the next is the sigmoid function, okay. We can declare this above the feed forward, okay. This is the function of sigmoid, okay. If it is true, this is this one. If not, return this value. This is all the definition of sigmoid function, okay. This will be called like this one, okay. When we call the function sigmoid, it will do this operation, and then the value will be obtained. Then the next propagation is just propagate the obtained error from the output up to the input layer, okay. So during the backward propagation, the first thing is the error is done by comparing the desired value minus the obtained value during forward propagation, okay. And then this output delta value will be done by this value, the first obtained value times the sigmoid of the output value, okay, y1 and y2. And the next is self dot z error value is output dot delta value. This value that is going to be given to the hidden layer will be multiplied by or dot product with the second weight transpose, okay. And the next is the magnitude of self dot z2 delta will be the error times the sigmoid of self dot z2, okay. This is propagated from the hidden layer to the input layer, okay. So the next update of the weight, okay, because to decrease the errors you have to update the weights, and then after feed forward and back propagate, the error get is lesser than the obtained error, that is during feed forward propagation, okay. So how we can update the error? First of all, this w1 will be updated. Self dot w1 is equals to w1 plus the transpose of the input, okay, dot with this z2 delta, okay. And this w2 will be updated having self dot z2 as output, okay. Transpose times dot product with self dot output delta times the learn coefficient, okay. And in the like, we will multiply sum of this one times and self of b2 or the bias, the second bias can be updated like this one, okay. So after updating this b1 and the b2 value, so the next step will be plotting the graph, okay. So to plot the graph, we will declare a function plot error having x-axis and y-axis, having this magnitude, okay, x-axis with 100 and y-axis color blue, and the line width to of the graph is 3, and then x label is having the iteration, y label error, and the title is error graph, okay. And then we will call the function plot show, and this one is just nothing but show the weight values during the initial value when that is I is equals to 0, and the when I is equals to 10, and the last, that is when I is equals to this value. The final weights will be generated here. So we will train the network here, that is for I in range 2000. We can say any value here. This is for example when we take the range that is from I equals 0 to 2000, okay. Or we can give any value that is this one is the epoch value, okay. And this one is just having this if we get this error value, then to print, else to break and leave. Let us run the file and let's see the output value. Okay, so as you can see here, the output value, okay, here it is. The initial weights are this one. The okay, here we have the output value, that is actual value, that are 0.75 and 0.5, 0.35, 0.8, 0.3, 0.65, and the final loss is this value, okay. Since we have restricted the iteration, that's why it is this much very large error, okay. And the predicted output will be this one, that is 0.157 and extra. So this one, and the plot value will be seen here, okay. This is the error graph, okay. Here is the error graph, and that is the y-axis would be the error, and the x-axis would be the iterations. So we have designed the network like this. If you have any question, feel free and just put in the comment part. I have also a C++ code for this, so if you want it, don't hesitate to put your email in the comment part again. Thank you for watching. See you in the next video.